So what are threads? A thread is a basic unit of execution flow. Really, this is a sequence of instructions done with a program, and the CPU is going to run these on a scheduler. So it's a unit of executions, meaning, say you have a function call and you have a few things that you do in that function call. Well, that set of things you do, those tasks, that could be considered a thread if implemented a certain way, as we'll see. A thread has an execution context. This is state associated with that thread. This execution context is the information that a CPU needs to be able to execute these instructions. So let's illuminate this with an example. Say you're reading a book and you want to take a break, and to resume where you left off, you'll write down the page number, the line number, and the exact word you were at. This is your execution context. Now, if you were a more practical person, you'd probably just use a bookmark, but we're making analogies to computing here, so we need to be very precise. Now, you're reading your book, you set the book down because you're hungry, and you decide, I'm going to go into the kitchen and eat a snack. Now, you go off into the kitchen, you eat a snack, and you think, I'm satisfied now, I've eaten enough, and I want to go back and read my book. So you go back to the living room where your book was set down, you pick it up, and with that execution context, you know where you left off, and you resume reading the book. In this example, you are the CPU, and the tasks, the threads that you have scheduled, are reading a book and eating a snack. Now notice about this. With threads, they run concurrently. We'll have a separate video wholly dedicated to concurrency versus parallelism. That is something that beginners tend to get really caught up on. I want to make sure that that's very clear. But for now, we're talking about concurrency. And this is where, say, reading a book and eating a snack in the kitchen, you cannot do these things simultaneously. You cannot be in the kitchen and the living room at the exact same time. These are two totally different execution contexts. They are different units of execution flow. They're going to happen technically sequentially. However, if you were to tell someone what you did today, you could say, well, this morning I read a book and I ate a snack. It may seem that you did these things at the same time, or rather you did them within a certain arbitrary time frame. And this is very much similar to what happens with threads being scheduled on the CPU, where the CPU appears to be performing multiple computations at once, but it's not. It is switching between these. It does this by spending a small amount of time on each execution, on each thread. And this is possible, again, because of these separate execution contexts. The CPU has some context, some information about each of these tasks, these threads, and it knows how to kind of work on them a little bit at a time and switch back and forth between them. This point is going to come up again and again throughout the series when we talk about threading and concurrency, because threading owes itself to a certain type of tasks. There are some tasks that are not really befit for threading and concurrency, and we'll learn about that and why throughout this series. I think I really want to focus on that because that was a point that I was personally really confused about when I first learned about multi-threaded programming. I was often really confused why people would say, don't do file I/O with threads, it's bad, and they would never say why. This execution context and context switching is what we call it, switching between these contexts. This is really the crux of everything. There's certain expenses associated with switching between these contexts so quickly. We'll dive into that again later, but for now, this is possible. We're able to do threading on the CPU because of these separate execution contexts. And if you want to get really technical, you want to know exactly what an execution context is, tangibly, it's an independent set of values for a CPU's registers. I won't belabor that point. CPU theory is probably for a different series altogether, but if you want to know technically what an execution context is, it's really the state in the CPU's registers. Now we'll look at a process. We'll zoom out a little bit. So a process is a set of resources associated with a computation. What does that mean? Well, say you have a C program, and you compile that C program and you execute it. What's going to happen is a system call called fork is going to be sent to the kernel, and it's going to tell the kernel, hey, I want to run this program. Can you set up a little sandbox for me to run this program in? And the kernel will say, sure, let me grab some memory pages. Let me allocate some heap memory for you. You're going to have kind of your own resource space over here just for you. And these resources can include, again, memory pages. It could be file descriptors, open sockets, etc. Now, a process has at least one thread. What would this be with our C program example? Well, in a C program, you know the entry point to every C program is the main function. And when the main function executes, that is a thread. That is called the main thread. So every process has at least one thread. That would be the main function in the case of a C program. So process, threads, they're different. Multi-processing versus multi-threading are different. We'll have a few videos where we touch on multi-processing and fork and when you would want to use it and when you would not want to use it. But for now, let's not confuse the two. We're talking about threads here, and threads are going to exist within a process. So let's take a look at an illustration. So here we have a process, this blue globe, and within this process, over the course of time, we have different threads executing. And so if these were scheduled on the CPU, you would see here that the CPU switches between these tasks, these threads, over the course of time. And you'll notice here that none of these threads overlap one another in terms of their execution duration. So you don't have thread 1 and thread 2 running at the same time. Now, if you were to zoom way out from this and look at this as some infinitesimally small amount of time, it may appear that all three of these threads are running at the same exact time. And this is of great benefit to us when we talk about concurrency, because maybe there are certain tasks that typically would be blocking, but with threading, we could do a little bit of work here, a little bit of work there, a little bit of work over there, and we'll be switching back and forth between those. And again, processes can have many threads, as we just saw. And I touched on this a little bit, that threads may create other threads. So you could have your main function in a C program, the main thread, and that main thread could create a child thread. And inside that child thread, you could create a grandchild thread. So the child thread could create its own child thread. So let's write some code.